In this short video, we just want to talk about one more mathematical treatment of these Michaelis-Menten enzyme equations. And we're going to look at what we call Lineweaver-Burk plot. So if you remember, the Michaelis-Menten equation is hyperbolic. So we have this equation down here in the bottom right, and we can look at the velocity. Remember, that's reaction rate. The maximum velocity, and if you remember, the maximum velocity is equal to that kcat times the enzyme total times substrate concentration over substrate plus that Michaelis-Menten enzyme, or Michaelis-Menten constant. Michaelis-Menten constant and kcat really tell us a lot about our enzyme. They describe our enzyme. Vmax can vary because this enzyme total, right, the amount of enzyme can vary. But kcat and km are really going to give us some important information about our enzyme. Now, a challenge here is that if we want to know Vmax, our graph never actually gets there, right? It approaches that asymptote, but it doesn't get there. We could use a computer model to estimate that value, which then we could plug in so we could solve for kcat. Or we can take what we call a double reciprocal plot and essentially invert both sides of our equation to get this new equation. So if we go back up here, I'm starting with this equation right here, and I'm going to invert both sides. So now instead of velocity, I've got 1 over velocity, and instead of this, I have this, which looks a little weird, but try it. You can flip this, do some algebra, and we're going to get this. And we like this a lot because look at that. Y equals mx plus b. This gives us a straight line form. So let's take a look at what that would look like graphed. Y equals mx plus b. So if I'm going to graph, I'm going to graph on the y-axis instead of velocity, 1 over the velocity value. And on the x-axis, instead of substrate concentration, 1 over substrate concentration. And I get a straight line graph. I could calculate my slope from the graph, and I know my slope would be Km over Vmax. I know my y-intercept right here is 1 over Vmax. So if I can read that y-intercept off the graph, I can solve for Vmax. So now, if I've calculated my slope from the graph, I've solved for Vmax, I can now find that Michaelis-Menten constant. And with a little more math, you'll find that your x-intercept is negative 1 over km. Let's look at that just real quick. It's always nice to know that the math actually works. So if I look at this equation and I want to look at my x-intercept, so I'm looking where y is 0. So y is this whole thing right here, 1 over v. I'm going to plug in 0 for that. So I have 0 equals Km over Vmax times 1 over substrate plus 1 over Vmax. All right, I can solve this. All right, so I've got Km over Vmax times 1 over the substrate equals negative 1 over Vmax. And you know what? This Vmax is going to cancel on both sides nicely. So I'm left with Km times 1 over S, right? Km times 1 over substrate concentration equals negative 1. This X is 1 over substrate. So I want to solve for this because I want to see where I'm going to cross. So I got to divide both sides by that Km value. And now, let me change color. So I'm going to have 1 over the substrate is negative 1 over Km. And remember, this is only when we're at that x-axis, that x-intercept. And hence, if I can read this value here off my graph, I can now calculate my Michaelis-Menten constant. So Lineweaver-Burk allows us to plot data and then read these 3 really important values for our Michaelis-Menten enzyme off the graph. We can find the Vmax, we can find Km, and we can find Kcat. And you'll have a chance to practice that on the homework.